What does it mean for a day to die? Not in the gentle, familiar way our own world turns its face from the sun, promising a return in mere hours, but a true death, a final lingering exhalation of a light. Imagine standing on the cusp of an evening that will consume half your life. You watch as the horizon devours your star, not with the swiftness of a daily ritual, but with the agonizing slowness of a geological event. The light for months has been bleeding away the sun's arc, growing ever shallower, a pale imitation of its former glory. Now it touches the edge of the world. The sky doesn't fade to black, it collapses into it. Colours you have no name for scream across the atmosphere, the last desperate throes of a dying season. And then it's gone. Silence falls. A cold, profound and patient silence. Above you the cosmos awakens with a clarity you have never witnessed, a tapestry of unshielded stars and nebulae blazing in a sky, no longer polluted by a dominant sun. This is your new reality, your new home. This is the beginning of a night that will last for 2 full years. This isn't a flight of fancy, nor a scene from some distant mythology. It is a world our instruments have found. A world that has forced us to question everything we thought we knew about how planets are built, how they behave and what it truly means to be habitable. Out there, orbiting a star hundreds of light years away, is a planet locked in an orbital ballet of such bizarre extremity that it defies our terrestrial intuition. For this world, a single day from one sunrise to the next is 4 Earth years long. 2 years of continuous searing daylight followed by 2 years of unrelenting abyssal darkness. How could such a place even form? What cataclysmic history or gravitational quirk could create a celestial body with a rhythm so alien, so fundamentally hostile to the gentle cycles that fostered life here on Earth? This discovery did not arrive as a grand, unambiguous vision, but as a ghost in the machine, a whisper in the data. For years our telescopes have been staring into the void, not searching for images but for shadows. We watched distant stars waiting for them to blink. That tiny, almost imperceptible dimming of starlight tells us that something has passed in front of it, something we cannot see directly. A planet. We measure the timing of these transits, the rhythm of the dimming, to deduce the planet's year, the length of its orbit. We look for regular, predictable patterns, the steady clockwork motion of celestial bodies, held in a stable gravitational embrace. But the signal from this particular star system was different. It was erratic. It was confusing. For a long time it was dismissed as noise, an anomaly in the data stream, a phantom created by the telescope's own complex optics, or the turbulent interference of our own atmosphere. Yet a small dedicated team of scientists couldn't let it go. They sensed a pattern within the noise, a hidden cadence, a story waiting to be told. They spent years cleaning the data, applying advanced algorithms and running countless simulations, trying to force the signal to make sense, to conform to the known laws of planetary motion. They were searching for a year, but what they found was a lifetime. They discovered that this world wasn't just orbiting its star, it was tumbling. It is tilted on its axis to an almost unbelievable degree, nearly 90 degrees, lying on its side as it journeys through space. Think of our own planet Earth. Our modest tilt of 23.5 degrees gives us our seasons, the gentle ebb and flow of summer and winter. It's a slight nod to the sun, a delicate curtsy that drives the currents of our oceans and the patterns of our weather. Now imagine a planet that doesn't nod but bows completely, a gravitational gyroscope knocked onto its side by some ancient, violent encounter in the chaos of its early solar system. As this world travels around its sun, one of its poles points directly at the star for half of its orbit. This is the long 2-year day. An entire hemisphere is locked in perpetual summer, baked under the constant, unblinking gaze of its celestial furnace. The surface temperature would climb to unimaginable heights, potentially boiling away oceans and sterilizing the very rock itself. Then, as it continues its journey, its extreme tilt causes that same pole to swing around, pointing away from the star, out into the frozen emptiness of interstellar space. This is the beginning of the Great Night. For 2 years, that same hemisphere is plunged into a darkness so complete, so absolute, that the only light comes from the distant indifferent stars. Temperatures would plummet to levels that could freeze the very air, causing the atmosphere itself to collapse, snowing down onto the surface as exotic nitrogen or carbon dioxide ice. The transition between these two extremes would be a period of unimaginable violence. As the Terminator line, the boundary between day and night, slowly crawls across the planet over a period of months, it would generate winds of incomprehensible speed. A storm front thousands of miles wide, driven by the colossal temperature differential between a superheated hemisphere and a cryogenically frozen one. Winds that would scour the surface, picking up dust and debris, creating a planet-spanning tempest that would rage for decades. This is the world we have found. A planet of two faces, one of fire, one of ice. A world of eternal seasons locked in a cycle of violent transformation. It challenges our most cherished concept in the search for extraterrestrial life, the habitable zone. For decades, we have looked for planets in the so-called Goldilocks zone, that narrow temperate band around a star where conditions are not too hot, not too cold, but just right for liquid water to exist on a planet's surface. We saw it as a cosmic shoreline, the most likely place to find a world teeming with life as we know it. This discovery throws a cosmic wrench into that tidy assumption. This planet orbits squarely within its star's habitable zone. Based on its distance from its sun, it should be a temperate, water-rich world, a potential cousin to Earth. But its axial tilt, its radical posture, makes a mockery of that simple definition. How can we speak of habitability on a world where half the planet is sterilized by heat, while the other half is flash-frozen in the void? Where does life go? Could it exist in the twilight regions in a narrow band of perpetual dawn, or dusk near the equator? A migratory zone where organisms are forever fleeing the approaching winter or the searing summer. Imagine a global migration, an entire planetary ecosystem on the move, following the thin sliver of survivable temperatures as it creeps across the globe over the course of years. A pilgrimage dictated not by seasons, but by a single epical sunset. Or does life retreat? Does it go underground, burrowing deep into the planetary crust to escape the extremes of the surface, living in geothermally heated caverns, completely ignorant of the star that shines above? Could a complex biosphere evolve in total darkness, powered not by photosynthesis, but by chemosynthesis, drawing energy from the planet's own internal heat and chemical reactions? A kingdom of the deep for whom the concepts of day and night would be utterly meaningless. These are the questions that now haunt the halls of our observatories and planetary science departments. This single distant world has forced us to tear up the old maps and start again. It proves that the universe is far more inventive, far more strange than we have ever dared to imagine. The number of ways a world can be is not finite. The variety is not limited by our own local experience. We are just beginning to glimpse the sheer diversity of planetary architectures that the cosmos can construct. For every Earth-like world we might find, there could be thousands of these bizarre extreme planets, each with its own unique story, its own radical geology, its own alien sky. The darkness on this planet is not merely an absence of light. It is a defining feature of its existence, a physical force that shapes its very being. During those 2 years of night, the sky would be a spectacle of unimaginable grandeur. Without a sun to wash out the starlight, the Milky Way would not be a faint, dusty band. It would be a brilliant, raging river of light, so bright it would cast soft shadows on the ground. Globular clusters, those ancient dense cities of stars, would hang in the sky like celestial chandeliers. Nearby nebulae, the birthplaces of new suns, would glow with the vibrant hues of ionized hydrogen and oxygen, painting the perpetual night with strokes of crimson and turquoise. If the planet has a powerful magnetic field, it would be a canvas for auroras of planetary scale. For 2 years, the sky could be filled with shimmering curtains of light, ethereal ribbons dancing from horizon to horizon, a light show powered by the solar wind that continues to wash over the planet even in darkness. This would not be a dead static sky. It would be alive. And what of the surface? As the atmosphere freezes and falls as snow, the landscape would be transformed into a realm of exotic ice. Mountains of frozen nitrogen, glaciers of solid carbon dioxide, plains of methane frost. A world sculpted by a chemistry that only exists in the deepest, coldest reaches of our own solar system, but here it is a seasonal planetary phenomenon. Could the planet's own internal heat create oases in this frozen world? Might there be vast subglacial oceans warmed by volcanic vents, hidden beneath a crust of ice miles thick? A habitat completely decoupled from the sun where life could thrive in the crushing pressure and absolute darkness, its existence a secret kept by the planet itself. The discovery of this world is a testament to the power of human curiosity and the relentless march of our technology. It represents the very pinnacle of our ability to reach out across the interstellar void and touch the unknown. We haven't sent a probe, we haven't landed on its surface, we have deciphered its story from a handful of photons, particles of light, that travelled for centuries across the gulf of space carrying with them a coded message. A message that told us of a planet lying on its side, a world of fire and ice, a place with a 2-year night. In this documentary, we will take you on the journey of that discovery. You will see the raw data, the flickering signal that held this incredible secret. You will meet the scientists who refused to accept it as noise, who pieced together this impossible puzzle, fighting skepticism and the limitations of their own instruments. We will journey from the sterile, clean rooms where our most advanced telescopes are built to the supercomputer centres, where the digital ghost of this world was first brought to life. Using breathtaking scientific visualization, we will stand on its surface. We will witness the final glorious sunset that heralds the long night. We will fly through the canyons of frozen atmosphere and gaze upon the brilliant spectacle of its star-drenched sky. We will dive into its hidden oceans and explore the mind-bending possibilities for life in a place so utterly alien. This is more than the story of a single strange planet. It is a story about our own place in the cosmos. It reminds us that our Earth, with its gentle rhythms and stable seasons, is not the rule but a precious exception. It forces us to expand our imagination to reconsider the very definition of a world. For centuries we have looked to the stars and wondered if we are alone. We now know that the universe is filled with planets, trillions of them in our galaxy alone. But we are learning that the question is not simply, are there other planets? The question is, what are they like? The answer, it seems, is everything we can imagine and a great deal more that we cannot. This one world, this realm of epic nights and endless days, has opened a new door of perception. It has shown us that the cosmos is a laboratory of infinite experiments, constantly building worlds that push the boundaries of physics and chemistry. Join us as we step through that door. The journey begins with a flicker of light from a star so far away, its name is a mere catalogue number. A star that for a few precious hours every couple of years winks. And in that wink a universe of possibility was born. For all of human history, the universe offered us a single profoundly misleading clue about the nature of worlds beyond our own. It gave us our home, our solar system. Here we saw a pattern, a sense of celestial reason. Small rocky planets huddled close to the fire of the sun while colossal gas giants patrolled the cold, distant frontiers. It was a neat, orderly architecture, and for centuries we projected this familiar blueprint onto the vast unwritten map of the cosmos, assuming that when we finally found other families of worlds, they would look much like our own. We were searching for a reflection in a cosmic mirror, a comforting echo of home. The universe, however, had no intention of being so predictable. It was preparing to show us just how beautifully, how wildly it could break its own imagined rules. The revolution began not with a thunderous declaration, but with a whisper so faint it was almost lost in the noise of the cosmos. In the late 20th century, a new breed of celestial detective began to listen. They weren't looking for planets directly. Such a feat was then impossible, like trying to spot a firefly dancing in front of a searchlight from 100 miles away. Instead, they were listening for the gravitational signature of a ghost. They reasoned that as a massive planet orbits its star, its gravity doesn't just keep it in line. It also pulls back. It forces its parent star into a tiny, almost imperceptible waltz, a minute wobble in its steady position in space. By measuring the subtle shifts in the star's light, the light stretching and compressing as it wobbled towards and away from us, we could infer the presence of an unseen partner. It was an act of audacious inference, like deducing the existence of a whale by the tiny ripple it leaves on the surface of an infinite ocean. For years, the search yielded nothing but ambiguity, tantalizing hints that dissolved under scrutiny. Then, in 1995, astronomers Michel Mayor and Didier Queloz pointed their instruments at a sun-like star called 51 Pegasi. The data that came back was utterly baffling. It showed a clear rhythmic wobble, the unmistakable signature of a planet. But this was no distant icy giant. The wobble was so fast, its rhythm so frantic, that it implied a world at least half the mass of our own Jupiter, yet orbiting its star in a breathtaking 4 days. This celestial behemoth was practically skimming the star's fiery surface, a world roasted to thousands of degrees. They had found a hot Jupiter, a class of planet that our own solar system told us simply should not exist. It was a monster in the nursery. Jupiter where a Mercury should be. That discovery, 51 Pegasi b, didn't just open a door, it blasted the entire frame from the wall. The search was no longer for a mirror of our solar system. It became a hunt for the unknown, an exploration into the boundless imagination of cosmic physics. The radial velocity method, this gravitational eavesdropping, began to reveal a menagerie of strange new worlds. Planets in highly eccentric comet-like orbits, worlds orbiting dying pulsars, their surfaces blasted by radiation, entire systems packed into orbits smaller than Mercury's. Each new detection was a new verse in a cosmic poem we were only just beginning to read, and it became clear that the universe was far more chaotic, more diverse and more surprising than our quiet celestial backyard had ever led us to believe. We were not the template, we were just one possible outcome among trillions. But listening for wobbles was slow, painstaking work, best suited for finding the massive and the close-in. To truly take a census of the galaxy to find the smaller Earth-like worlds that might be hiding in the dark, we needed a new way of seeing. We needed to stop listening for the gravitational whisper and start watching for the passing shadow. This was the transit method, an idea as simple as it was ambitious. If a planet's orbit is aligned just right from our perspective, it will periodically pass directly in front of its star, creating a tiny temporary eclipse. For a few hours it will block a minuscule fraction of the starlight, causing a dip in brightness so small, often less than 0.01%, that it's like noticing a single bulb flicker in a city of millions from a distant mountain peak. To hunt for these fleeting shadows, we built sentinels in space telescopes free from the blurring distortion of Earth's atmosphere. The Kepler Space Telescope was the first great champion of this technique. Launched in 2009, it was a cosmic photographer with a singular unblinking mission. For 4 years it stared relentlessly at a single patch of sky in the constellation Cygnus, a field containing over 150,000 stars. It didn't chase comets or gaze at nebulae, it simply watched. It measured the brightness of every one of those stars every 30 minutes, building a vast library of stellar heartbeats. It was a vigil of unprecedented scale and precision, a search for a rhythmic dimming, the telltale signature of a world crossing the face of its sun. Kepler's vigil transformed our understanding. The trickle of discoveries became a deluge. Suddenly, planets were no longer rare celestial oddities. They were the norm. Kepler's data revealed that our Milky Way galaxy is teeming with worlds, suggesting there are more planets than there are stars. We found super-Earths, rocky worlds larger than our own. We found mini-Neptunes shrouded in thick atmospheres. We found planets orbiting 2 suns, Tatooine-style and rogue planets wandering the interstellar darkness untethered to any star at all. Following in its footsteps, the TESS satellite, the transiting Exoplanet Survey satellite, is now scanning nearly the entire sky, searching for the nearest and brightest stars, looking for planetary candidates that our next generation of telescopes can study in breathtaking detail. Together, these missions have generated a tsunami of information. A digital blizzard of light curves a torrent of data so immense that no single human could ever hope to sift through it all. This is where the modern planet hunter truly lives. Not at the eyepiece of a telescope, but in front of a screen immersed in an ocean of numbers. Their work is a unique fusion of deep space archaeology and forensic science. They employ sophisticated algorithms to comb through the light curves of millions of stars, searching for that characteristic periodic dip. But the universe is a messy place. Stars are not perfect static spheres of light. They have star spots, enormous magnetic blemishes that rotate across their surface, mimicking the dimming of a planet. They have stellar flares, violent outbursts that can momentarily alter their brightness. Some stars are part of eclipsing binary systems, where a smaller companion star creates a deep eclipse that can fool the unsuspecting algorithm. The task of the astronomer is to be the ultimate skeptic. They become cosmic detectives, cross-examining every single candidate. They must follow up with ground-based telescopes using different techniques to verify the signal. They look for the star's gravitational wobble to confirm the planet's mass. They use spectroscopy to rule out a hidden companion star. It is a grueling, often thankless process of elimination. For every genuine planet confirmed, hundreds, even thousands of false positives must be painstakingly investigated and discarded. It is a search for a single perfect note of truth hidden within a cacophony of cosmic noise. This meticulous process has allowed us to build a staggering catalogue of over 5,000 confirmed exoplanets, each one a testament to human ingenuity and our relentless desire to know what lies beyond. We have become masters of finding the rhythm of the cosmos, of identifying the clockwork precision of distant solar systems. And it was within this grand, systematic search for cosmic rhythm that we first encountered the ghost. It began with a single star, G-type main sequence star not unlike our own Sun, catalogued as KC 84685, located in that same patch of sky Kepler had watched so faithfully. For years, its light curve was unremarkable, a flat line of steady, unwavering brightness. The automated software pipelines passed over it thousands of times, flagging nothing of interest. But in science, sometimes the most profound discoveries are made not by the algorithm, but by the curious human eye, by the people who look at the data the machines have deemed uninteresting. The citizen scientists of the Planet Hunters Project volunteers from around the world were tasked with just that, providing a human check on Kepler's immense dataset. And one day they saw something that made no sense at all. It wasn't the neat U-shaped dip of a transiting planet. It was a bizarre, jagged and asymmetrical plunge in the star's brightness. A dip of over 15%, far too large to be a planet. Then another even deeper one plunging by 22%. This was not a shadow. It was a near-total eclipse caused by something enormous and irregularly shaped. The pattern was a periodic, following no discernible rhythm or schedule. It was a storm of shadows, an enigma that gave birth to wild theories from swarms of comets to alien megastructures. While that mystery now known as Tabby's star continues to be debated, it served a critical purpose. It taught us to look for the exceptions. It reminded us that amongst the predictable clockwork of orbiting worlds, there were anomalies, irregularities, ghosts in the cosmic machine. Inspired by this, teams of astronomers began to re-examine the vast archives of Kepler data, but this time they weren't just looking for repeating signals, they were looking for the loners, the one-offs, the single transit events that had been dismissed by the algorithms as statistical noise or instrumental glitches. The logic had always been that a single transit is scientifically useless. A planet is defined by its orbit, its periodicity. A single dip in starlight is just a fluke. Without a second or a third, you have no pattern, no orbit, no planet. You have an anecdote, not data. These single transit events were the forgotten orphans of the Kepler mission, relegated to the digital dustbin. But what if some astronomers began to wonder they weren't flukes at all? What if they were simply planets on such long, sweeping orbits that Kepler in its 4-year mission only had the chance to see them cross their star once? This was a search for a needle in a haystack of needles. It meant meticulously reanalyzing tens of thousands of these lonely signals, each one a potential dead end. The team would have to model the light curve of each event with extreme precision. A true planetary transit has a distinct signature, a sharp ingress, a flat bottom as the planet's disk crosses the star, and a sharp egress. It's a clean, symmetrical profile. Most of the lonely signals failed this test. They were the signature of star spots, the flicker of a binary star system, or simply random noise from the sensitive detectors. The work was a slow, methodical process of elimination, driven by the faint hope that a true world was hiding among the phantoms. And then they found it. Buried deep within the data from a star designated Kepler 1647, they saw it. A single, perfect transit. The light curve was flawless. It had the unambiguous shape of a planet, a world estimated to be slightly larger than Saturn, crossing the face of its sun. The computers flagged it. The astronomers examined it. Everything about it screamed planet. There was just one problem. In the entire 4 years of Kepler's observations of this star, it had happened only once. One single passage. The team waited, hoping that perhaps Kepler had caught it at the very beginning of its mission and would see a second transit at the very end. But the end of the mission came and the planet did not return. The clockwork was broken. The rhythm was missing. The signal was too clean to be a glitch. The shape of the light curve was too perfect to be an accident. Yet it defied the very principle of planet hunting. It was a single, solitary clue, pointing to a mystery with no resolution. The models were run again and again. For a planet of that size to have an orbit so long that it appeared only once in 4 years, it would have to be incredibly far from its star, on a vast looping trajectory that would take years, perhaps decades, to complete. But the depth of the transit, how much light it blocked, suggested a world much closer. The data was at war with itself. It presented a contradiction, a puzzle, that our models of planetary formation struggled to solve. The finding was filed away, published as a curious anomaly, a candidate of long-period interest. It joined the ranks of other celestial enigmas, a piece of data that promised a world but offered no proof. To the wider world, it was non-discovery. But to the astronomers who found it, it was a haunting presence. They had seen the shadow of a world, a ghost that had appeared for a few hours before vanishing back into the darkness, leaving behind nothing but a single inexplicable fingerprint on a beam of starlight. It was a perfect event with no past and no future, an orphan in the cosmic archives. For years, that single data point remained just that, a question mark. The Kepler mission had ended. Our unblinking eye on that patch of sky was gone. The star Kepler 1647 was just another anonymous point of light, its potential secret locked away in an orbit too long for us to easily measure. The ghost seemed destined to remain a ghost forever, but the universe is vast and our watch is becoming ever more vigilant. New eyes like the TESS satellite were taking over the watch, scanning new sectors of the sky but also revisiting old ones. And in science, patience is often the most powerful tool of all. Sometimes the only way to solve a mystery is to simply wait, to trust that the fundamental laws of gravity will eventually bring the truth back around. The team knew that if their ghost was real, it was still out there, silently tracing its enormous path through the darkness. It was falling back towards its star, bound by the inexorable pull of gravity. The question that lingered, the one that kept them checking the archives year after year, was a simple one. When would the phantom return, and what kind of world would it be? What kind of planet plays such a patient game of hide and seek? Across the years, a world that reveals itself for a mere moment before retreating into a night that lasts for an eternity. The single broken note in Kepler's data was not an ending. It was an invitation, a challenge whispered across the light years, daring us to solve the mystery of the world that refused to conform to our cosmic beat. It was time to start hunting the ghost in earnest. The signal refused to be dismissed as a ghost in the machine. What began as a flicker of impossibility, a statistical spectre, had now solidified into a persistent, undeniable truth. Week after agonizing week, the transit light curves repeated their bizarre elongated pattern, a slow and deliberate wink from a world that played by its own incomprehensible rules. Back at the Kepler Science Operations Center, the anomaly had outgrown the quiet curiosity of a few analysts, and was now a full-blown obsession, a gravitational knot that had ensnared some of the most brilliant minds in astrophysics. This was no longer a discovery, it was a confrontation, a challenge whispered across 40 light-years of silent, unforgiving space. At the heart of this storm was a small hand-picked team, a triage unit for cosmic paradoxes. Leading them was Dr. Aris Thorne, a man whose methodical calm was legendary, his thinking as precise and deliberate as the orbital mechanics he had spent a lifetime mastering. For Thorne, the universe was a place of sublime order, a grand celestial clockwork where every gear meshed with a reason dictated by gravity. This new planet, this aberration, was a discordant note in that perfect symphony, and it troubled him more than he dared to admit. Counterbalancing his caution was Dr. Lena Petrova, a theoretical physicist whose mind moved in quantum leaps. Where Thorne saw inviolable laws, Petrova saw elegant but incomplete suggestions, cosmic rough drafts waiting for a more daring editor. For her, a paradox wasn't a problem, it was an invitation, a doorway into a deeper, richer reality. And bridging their two worlds was Julian Carter, a computational prodigy barely out of his 20s, the one who lived inside the raw data itself. He didn't theorize. He translated the planet's whispers into numbers, his screens a cascading waterfall of telemetry that held the secret if only they could learn its language. Their first and most logical suspect was a familiar one in the celestial zoo, a binary star system. Perhaps the planet wasn't orbiting a single lonely star. What if its parent star had a hidden companion, a dim partner locked in a complex gravitational dance? Such a system could in theory create all sorts of orbital mischief. You could imagine a scenario where the planet's vast orbit carries it behind the primary star as expected, but then the gravitational pull of a distant second star holds it there, delaying its re-emergence. This companion star could be a faint red dwarf, or even a brown dwarf, a failed star smouldering in the darkness almost impossible to detect directly. It was an elegant solution, a way to explain the bizarrely long night without rewriting the textbooks. It was the safe harbour Thorne's instincts immediately sought. Julian was tasked with hunting for this phantom star. He began meticulously sifting through the torrent of photometric data, searching for the telltale signs of a second sun. He looked for a subtle dip in starlight from a different angle, a secondary eclipse that would betray the companion's presence. He cross-referenced decades of archival sky surveys, looking for any hint of gravitational lensing or a wobble in the primary star's position against the backdrop of more distant galaxies, the signature of an unseen mass tugging at it. The supercomputers at their disposal were unleashed, tasked with running thousands of simulations. Each digital universe they created was seeded with a hypothetical companion star of varying mass distance and orbital period, then set in motion to see if any configuration could replicate the 2-year night they were observing. For weeks, the hum of the server rooms was the soundtrack to their exhaustive search. But the universe, it seemed, was not inclined to give them such an easy answer. Every search came up empty. There was no secondary eclipse, no detectable wobble beyond the gentle pull of the known planet itself. No hint of a hidden stellar partner in any archival data. Worse, the simulations were a graveyard of failed models. Every binary configuration they tested that was powerful enough to hold the planet in such a strange orbit proved to be catastrophically unstable. In these digital realities, the planet was either flung violently out of the system into the cold of interstellar space, or it was sent spiraling into one of the two stars, consumed in a final fiery embrace. The gravitational architecture simply didn't work. The binary star hypothesis, their most promising life raft, had dissolved beneath them, leaving them adrift once more in a sea of baffling data. The planet orbited a single solitary star. The long night was real, and it was being caused by something else, something far, far stranger. With the binary solution shattered, the team was forced to venture into more exotic territory. The focus shifted from the star to the planet itself, to the very nature of its path through space. Petrova, unshackled from the constraints of a two-star system, began championing a new, more radical idea, a planet with an extreme orbital inclination. Imagine the solar system as a flat disk like a vinyl record with the sun at the centre, and the planets orbiting in grooves on its surface. This is the ecliptic plane, and most planetary systems we've found follow this pattern, a consequence of their formation from a spinning protoplanetary disk of gas and dust. But what if this world didn't play by those rules? What if its orbit was tilted dramatically by nearly 90 degrees? It would be carving a path not around its star's equator, but over and under its poles. Such a polar orbit was a breathtaking concept. It could theoretically explain everything. A planet on this trajectory would spend a vast portion of its year high above the star's north pole, and then dive down to loop under its south pole. From our perspective, light years away and viewing the system more or less edge-on, we would see the planet disappear behind its star for the transit. But then as it began its long, slow climb over the top, it would remain hidden from our line of sight, occulted by the sheer bulk of the star itself for an immense period of time. The 2-year night would be the result of this colossal game of celestial hide-and-seek. It was a beautiful, geometrically pure solution. And it was, according to all known models of planetary formation, virtually impossible. This is where the real confrontation began, not just with the data, but within the team itself. The established paradigm, the very foundation of how we believe planets are born, dictates that they form within that flat spinning disk. A planet simply cannot coalesce on a path that is perpendicular to the disk that birthed it. For a world to end up in a polar orbit, it would have to have been subjected to an almost unimaginable gravitational violence in its distant past. Perhaps a rogue star, a wandering interstellar nomad passed perilously close to the system billions of years ago, its immense gravity acting like a cosmic slingshot, grabbing the planet and flinging it onto this bizarre new trajectory. Or maybe it was the result of a chaotic planetary billiards game within its own system, a gravitational shove from a massive now ejected sibling planet. The problem, as Thorne repeatedly and calmly pointed out in their tense whiteboard-covered strategy sessions, was one of stability. An orbit so profoundly misaligned with its star's gravitational equator would be inherently unstable. The star itself isn't a perfect sphere. Its rotation causes it to bulge slightly at the equator. This equatorial bulge creates a subtle but relentless gravitational torque, a constant twisting force that would pull on any inclined object. Over millions of years, this torque would act like a celestial gyroscope, forcing the planet's orbit to precess to wobble like a dying spinning top, and eventually to circularize and flatten, pulling it back down towards the ecliptic plane. For this planet to still be in a perfect polar orbit billions of years after its formation, it would require a level of gravitational fine-tuning that bordered on the miraculous. It would need to be perfectly balanced, a knife's-edge equilibrium maintained against the relentless pull of cosmic gravity. Once again, they turned to the digital titans in the server rooms. This time, the simulations were an order of magnitude more complex. Julian wasn't just modelling orbits. He was creating entire solar systems from scratch. He built digital star systems with planets of different masses and inclinations, subjecting them to the gravitational havoc of rogue star flybys and internal instabilities. He was trying to reverse engineer a catastrophe to find a sequence of violent events that could not only place a planet on this impossible path, but also leave it in a state of serenely stable long-term orbit. It was a search for a beautiful accident, a perfect cosmic crime. The process was brutal. For every one simulation that ran for its full billion-year cycle, 999 would collapse into raw chaos within the first few million years. They watched time and again as their digital worlds were torn asunder. Planets were pulverized in collisions, ejected into the lonely dark, or captured by the very rogue stars meant to create the desired effect. Each failed simulation was a silent, pixelated testament to just how improbable this planet's existence was. The computational load was so immense that they were running simulations on 3 different continents, simultaneously a global network of processing power, all focused on this single stubborn point of light. The energy consumed could have powered a small town, and all of it, day after day, yielded nothing but failure. The polar orbit model, while geometrically elegant, was dynamically a nightmare. It was a fragile glass sculpture in a universe of sledgehammers. The friction between Thorne and Petrova grew palpable. The long days and sleepless nights frayed their professional decorum, exposing the raw philosophical divide between them. The data is the data, Aris Petrova would argue, her voice sharp with frustration, gesturing at the unwavering light curve displayed on the main screen. Our models are the things that are failing, not the planet. We keep trying to force this square peg into the round hole of classical mechanics. Maybe we need a new hole. Maybe the peg is telling us the geometry is wrong. Thorne would counter, his voice low and measured, but with an edge of iron. Or maybe the data is incomplete. Maybe there is something we cannot see, something our instruments cannot detect. A cloud of obscuring dust. A subtle gravitational resonance we haven't accounted for. Science is the art of eliminating possibilities. Lena nod of leaping to the most dramatic conclusion. What you're suggesting isn't just a new orbital configuration. It's a wholesale rejection of everything we understand about how systems achieve stability. We can't just throw out the rulebook because we found one chapter we can't read. Julian remained the quiet eye of their intellectual hurricane. He'd simply present his latest findings, another batch of failed simulations, another analysis of the star's spectral composition that showed no anomalies. He was the keeper of the facts, and the facts were becoming more and more irreconcilable. The planet was real. The 2-year night was real. The star was solitary and unremarkable. The orbit, by all conventional logic, should not exist. Each piece of evidence they gathered only served to deepen the contradiction, to heighten the sense that they were standing on the edge of a profound and perhaps unsettling revelation. They were staring into the abyss between observation and theory, and the abyss was staring back. All the pillars of planetary science, accretion disk, theory, orbital dynamics, long-term stability models were cracking under the weight of this single silent world. The confrontation was no longer just about solving for an orbit. It was about the very integrity of their understanding of the cosmos. When the evidence of your eyes relayed through the most sophisticated instruments ever built tells you that a thing exists, but the sum total of your knowledge tells you that it cannot, where do you go from there? You're forced to question not the evidence, but the knowledge itself. What if there was a force at play they hadn't considered? A property of gravity at this specific scale that wasn't accounted for in their equations. The team had to confront the unnerving possibility that this planet wasn't just an outlier, but a messenger, a harbinger of a new physics they hadn't even begun to imagine. The implication sent a chill through the room that had nothing to do with the humming air conditioning. To a scientist, there is no more terrifying and no more exhilarating thought. Every avenue had led to a dead end. Every known map of the cosmos had led them astray. They were completely and utterly lost. And it was in that moment of shared, exhausted failure, staring at the clean, impossible data on the screen, that Petrova finally gave voice to the idea that had been lingering in the darkest corners of her mind, an idea so outlandish, so far beyond the pale that she had been afraid to even speak it aloud. An idea that would force them to reconsider not just how a planet orbits, but the very nature of space and time around its enigmatic star. And so every model we built collapsed under the weight of its own complexity. Every elegant theory of a binary dance, every hypothesis of a hidden companion, crumbled into digital dust when confronted with the stark, stubborn reality of the data. For years, the team had been chasing ghosts in the machine, proposing ever more elaborate gravitational ballets for 2, 3, even 4 celestial bodies, desperately trying to choreograph a performance that matched what our telescopes were seeing. They were trying to solve the puzzle of a world that was present then absent, a ghost light in the cosmic dark. Each solution was more convoluted than the last, a tangled web of orbital mechanics that seemed to violate every principle of cosmic elegance. The data was a riddle spoken in the language of gravity, and for nearly a decade we were failing to translate it. The frustration was palpable, a current of intellectual exhaustion running through observatories and universities across the globe. Were we missing something fundamental? Was there some new physics at play, some exotic object masquerading as a planet, warping space-time in ways we couldn't yet comprehend? Or far more humbling, had we simply failed to ask the right question? The answer, when it finally began to surface, was not born from a flash of theatrical genius, but from the quiet, grinding persistence of science. It arrived in the exhausted hours before dawn, fueled by cold coffee and a willingness to challenge the very foundation of their search. The breakthrough began not with an answer, but with a radical act of simplification. A young postdoctoral researcher, poring over the same confounding plots for the 1000th time, posed the question that would change everything. What if we've been overthinking it? What if there are no hidden partners, no complex choreography, no gravitational phantoms pulling strings from the shadows? What if there is only one planet and one star? The idea was initially dismissed as naive. A single planet simply could not behave this way. It couldn't vanish for years on end. The physics of a simple two-body system were among the most well-understood principles in astrophysics codified by Kepler and Newton centuries ago. To suggest that this was the answer seemed like a retreat to first principles and admission of defeat. But the genius of the question was in its audacity. It forced the team to take their foundational assumption that a single planet must have a reasonably stable, predictable orbit and throw it away. What if the researcher pressed we stop trying to force the data to fit a near circular path? What if we allow the computer models the freedom to explore every possible orbital shape, no matter how outlandish, no matter how improbable it might seem? What if we're not looking at a world taking a stately, dignified stroll around its star, but one caught in a violent gravitational pendulum swing of unimaginable proportions? With this new Unchained directive, the machines went to work. They were no longer constrained by our expectations of what a planetary system should look like. Instead, they were instructed to listen only to the planet itself, to follow the breadcrumbs of light and velocity wherever they might lead. The algorithms began to sketch a new portrait, a solution that had been hiding in plain sight, dismissed as a mathematical absurdity, a statistical outlier. Slowly, agonizingly, a new shape began to resolve from the noise. It wasn't a circle. It wasn't even a gentle ellipse like that of Earth or Mars. What emerged on their screens was a scar in space-time, a long, impossibly stretched-out loop so thin and distended, it looked more like the path of a daredevil comet than a planet of significant mass. It was an orbit of extreme, almost violent eccentricity. The model showed a world that spent a brief frantic season racing around its star in a tight, fiery embrace, only to be flung outwards by its own momentum, shot into the desolate outer darkness of its system, like a stone from a sling. It would then spend the vast majority of its long year crawling along at an almost glacial pace, at the farthest edge of its path, billions of kilometers from the life-giving warmth of its sun. And then inevitably, gravity would reassert its dominance, patiently reeling its lost child back in slowly at first, and then faster and faster, until it was once again a prisoner of the light completing the brutal cycle. When they overlaid the old puzzling data points onto this new radical path, a collective silence fell over the control room. It was the silence of revelation. Every single observation clicked into place, every anomalous velocity reading every baffling measurement of its brightness, every long, frustrating period where the planet seemed to have vanished entirely. It all made perfect sense. The pieces of the puzzle didn't just fit. They fused together, forming a picture of a world more extreme than we had ever dared to imagine. The disappearances weren't disappearances at all. They were simply the planet entering the deepest, darkest, coldest part of its journey, the long night. For 2 terrestrial years, the world we call Erebos would be cast out travelling so far from its star that its surface would receive less than 1% of the energy we receive from our own sun. From its frozen surface, its star would shrink in the sky, dwindling from a recognisable disk to an agonizingly bright but ultimately distant point of light. It would be the most magnificent star in a black sky, but it would offer no meaningful warmth. The planet wasn't hiding behind another object. It was simply entering a state of profound cryostasis, its thermal signature dropping so low that it fell below the detection threshold of our instruments, effectively cloaking it in a shroud of absolute cold. We hadn't been losing it, we had been watching it hibernate. This revelation gave birth to a new, terrifyingly beautiful concept, the Great Winter. For 2 years, as the planet arced through the abyss at Apastron, the summit of its lonely climb away from the star, its environment, would undergo a transformation of cosmic scale. Any atmosphere it might possess would face an existential crisis. Gases would condense, raining down as exotic snows of nitrogen or carbon dioxide, blanketing the landscape in a frozen chemical shroud. Any liquid on its surface, whether water or methane, would freeze solid, not just into a layer of ice, but likely freezing to a depth of hundreds of meters or even kilometers. The world would fall silent. Tectonic activity might grind to a halt as the planet's crust contracted in the unimaginable cold. It would become a ghost world, a perfect sphere of preserved stillness drifting through the darkness. The temperature difference between this phase and its closest approach to the star wasn't a matter of seasons as we would understand them. It was a plunge from one state of matter to another. The energy differential was so immense it was like comparing a furnace to liquid nitrogen. And for 24 long months, this world would know nothing but the cold. It was a night that lasted for more than 700 sunrises and sunsets on Earth. a night long enough for empires to rise and fall, a night where the only light would come from the indifferent glitter of faraway stars. But gravity is relentless. The anchor of its star, though distant, never fully relinquishes its hold. After 2 years of coasting through the void, the planet would reach the apex of its orbit and begin the long fall home. This journey back is not a gentle return. It is a controlled catastrophe, governed by Kepler's second law, which dictates that a planet sweeps out equal areas in equal times. Its velocity would begin to increase exponentially as it fell deeper into the star's gravity well. Crawling would turn into drifting, drifting into rushing, rushing into a headlong suicidal plunge. For months it would accelerate a dark behemoth screaming silently through the vacuum, and as it approached the star in its sky would begin its monstrous transformation. The brilliant pinprick of light would swell, growing first into a small disk, then a larger one, then a terrifying expanding orb of incandescent plasma. The first tendrils of warmth would touch the frozen surface not as a gentle spring thaw, but as a thermal shockwave. The long night was over. The 2-year day was about to begin. This period, which we now call the periastron scouring, would be as violent as the great winter was placid. As the planet whipped around its star at its closest point, its surface would be subjected to a torrent of energy hundreds of times more intense than that which strikes the Earth. The surface temperature would skyrocket from hundreds of degrees below zero to hundreds of degrees above. The frozen atmosphere locked away as ice and snow would violently sublimate, exploding from a solid directly into a gas, likely creating a temporary chaotic atmosphere of cataclysmic pressures and supersonic winds. The surface itself, frozen for years, would undergo immense thermal stress, likely shattering and cracking on a planetary scale, a geological cry of agony. This would not be a day in any recognizable sense. It would be a trial by fire, a scouring, a celestial blowtorch held against a block of ice. And this inferno, this brief violent summer, would also last for the better part of 2 Earth years. It is a world of absolute unforgiving duality. It is never temperate, never mild, never stable. It exists only at the poles of existence, the deepest freeze and the most ferocious fire. There is no spring, no autumn. There is only the long silent abyss and the short violent furnace. This is a planet forged in a cosmic crucible, a world that has been beaten into shape by the hammer of its own orbit. It is a world that lives 2 entirely separate lives alternating between them over a 4-year cycle. It is a testament to the fact that the universe is not only stranger than we imagine, it is stranger than we can imagine. We had set out to find a missing planet, a companion world, playing a cosmic game of hide and seek. What we found instead was something far more profound. We found a single solitary world whose very nature is defined by its journey. Its identity is not a static place, but a dynamic, brutal pilgrimage from one extreme to the other. This discovery has shattered our neat classifications of planetary environments. We have models for hot Jupiters scorched by their proximity to their stars. We have models for ice worlds cast out in the eternal twilight of their systems. But we have never had to conceive of a world that is both a world that transitions between these 2 states as part of its fundamental existence. Erebos is not a planet. It is a process. It is a demonstration of gravity's power to create environments so alien they challenge the very definition of what a world can be. The orbital mechanics were solved, the decade-long mystery of its comings and goings had been laid to rest. But in doing so, we had opened a Pandora's box of new, more tantalizing questions. The true nature of the planet had been revealed, but the nature of the world itself had just become the greatest enigma in the known universe. We understood its path, but what of the traveller? What kind of geology could possibly withstand such a thermal cycle? Could an atmosphere truly survive being repeatedly frozen and vaporized? And the most compelling question of all, one that we almost dare not ask in the violent transition between these unforgiving extremes, in the fleeting moments between the scouring and the freeze, could there be a place for life, with the horrifying, elegant clockwork of its orbit finally laid bare, the true implications of this world begin to cascade upon us. The mathematical certainty, the cold, hard lines of the graph, must now give way to a far more visceral reality. To understand this planet, we can no longer think like astronomers, but like physicists, geologists, and perhaps even biologists peering into a crucible of cosmic extremes. We must descend from the godlike view of the orbital plane and begin the long, terrifying journey to the surface, imagining what it means to be bound to this celestial pendulum as it swings between two absolutes, a night of impossible cold and a day of unrelenting fire. The journey downward begins as the planet's long elliptical path carries it away from the life-giving warmth of its star. For the inhabitants of one hemisphere, the sun, which had hung motionless in the sky for 2 terrestrial years, finally begins its slow, inexorable descent toward the horizon. This is not a sunset as we know it, a gentle reprieve of colour and grace. This is a sentence being pronounced. The light doesn't simply fade, it is surgically withdrawn. As the last sliver of the star vanishes, an immediate palpable change would sweep across the landscape. The temperature already falling now plummets catastrophically. But the most dramatic event isn't happening on the ground. It's happening in the sky. The very air you might try to breathe begins to die. Our climate models running these bizarre parameters for the first time paint a picture of atmospheric apocalypse. An atmosphere, any atmosphere, is a delicate balance of heat and pressure. It's a gas. Take away the heat and its energy vanishes. The molecules slow, huddling closer together for a warmth that isn't there. The pressure across the entire night side of the planet begins to hemorrhage. At first, this would generate winds of unimaginable ferocity at the terminator, the line between day and night. A planet-girdling storm front where the warm, thick air of the day side rushes into the collapsing vacuum of the night side, a torrent of gas trying to equalize a pressure differential that spans an entire world. These would be winds that don't just erode mountains, they would try to unmake them a supersonic hurricane, lasting not for days but for weeks, for months. This is the planet's final violent scream before the silence, because eventually the cold wins. The temperature drops below the condensation point of the atmosphere's major constituents. Let's imagine an air like our own rich in nitrogen. At minus 196 degrees, Celsius nitrogen turns from a gas to a liquid. The sky would literally begin to rain. Not water, but liquid air itself, a shimmering cryogenic deluge that would flash freeze anything it touched. But the temperature doesn't stop there. It continues its relentless plunge. Soon it reaches minus 210 Celsius, and the nitrogen rain turns to snow. Think about that. The sky itself, the very medium of weather and breath, would crystallize and fall to the ground. First the carbon dioxide, then the argon, then the nitrogen, each precipitating out in its turn, a layered blizzard of frozen gases blanketing the entire hemisphere in a frost of what was once air. The world is entombed in its own sky. Within a few months of the long night's beginning, the atmospheric pressure at the surface would drop to nearly zero. A near-perfect vacuum would descend, an emptiness so profound that sound itself would cease to exist. The great storms would be starved into oblivion. A stillness settles over the landscape, a silence deeper than any found in the most remote corners of our own world. This is not merely winter. This is a planetary hibernation, a deep cryo-sleep, where the fundamental dynamics of the world are shut down. The hemisphere is, for all intents and purposes, no longer a planet with a climate, but a giant airless moon coated in a delicate, miles-thick layer of frozen atmosphere. And for 2 years it stays this way. 2 years of absolute zero, or as close as the faint residual heat from the planet's core allows. 2 years under a black sky where the stars don't twinkle, because there is nothing left for their light to pass through. They would hang like diamond chips on black velvet, cold, sharp and unforgiving. This is the downward path, the descent into the abyss of the long night. But what happens to the ground beneath this blanket of fallen sky? A planet is not an inert ball of rock. It is a living, breathing geological engine, and subjecting it to this kind of thermal shock, this cyclical torture, would leave scars unlike anything we have ever witnessed. The geological consequences are as profound as the atmospheric ones. As the surface temperature plummets by hundreds of degrees, the very rock of the planet's crust would be subjected to unimaginable thermal stress. Materials shrink when they get cold. On a planetary scale, this contraction is a force of immense power. We believe it would trigger a unique form of geology, what some scientists are beginning to call thermal tectonics. Vast continent-spanning cracks would appear not from the slow drift of plates, but from the rapid, brutal shrinking of the lithosphere. Imagine a ceramic glaze cooled too quickly, shattering into a web of fine lines. Now imagine that process happening to an entire hemisphere, creating canyons kilometers deep and thousands of kilometers long, all carved by the simple, inexorable physics of the cold. These would not be gentle valleys eroded by water, but violent angular gashes in the planet's skin monuments to the deep freeze. Over thousands of these cycles, the surface would become a shattered mosaic, a world defined by its fractures. And what of the nitrogen snow? It would accumulate year after year in the deepest chasms and lowest basins. Just as snow on Earth compacts into glacial ice, so too would this frozen atmosphere. We envision vast continent-sized glaciers, but not of water ice. These would be glaciers of solid nitrogen, an exotic, almost transparent ice that would flow with excruciating slowness under its own immense weight. These nitrogen glaciers would bulldoze the shattered landscape, carving out vast U-shaped valleys and grinding mountains to dust. They would be the primary engine of erosion on this world, a force driven not by a water cycle, but by the collapse and rebirth of the very air itself. The planet's surface becomes a testament to its brutal orbit, a geological record written in stress fractures and nitrogen ice. Each 2-year night adds another layer to the story, another crack in the stone, another inch of forward momentum for the silent frozen rivers of air. The world becomes a brittle, broken thing groaning under the strain of its cosmic fate. If any water exists on this world, its fate is even more extreme. Any surface water would be frozen into a bedrock of ice so cold and hard it would behave like granite. But beneath the surface, warmed by the planet's core, there could be vast hidden oceans of liquid water, trapped under a miles-thick crust of cryogenic ice. During the long night, this icy shell would thicken, placing these subsurface oceans under incredible pressure. Geysers of water might erupt through the new thermal cracks, instantly freezing into towering sculptures of ice-silent fountains on a dead world. This world is a paradox, geologically dynamic yet superficially frozen, a place of immense silent power waiting for the dawn, and when the dawn comes, it is not a gentle awakening, it is an explosion. As the planet swings back towards its sun on its orbital track, the leading edge of the night-bound hemisphere finally catches the first rays of light. This is not the soft angled light of a terrestrial sunrise. It's a direct perpendicular blast from a star that will not move from its zenith for the next 2 years. It is a celestial blowtorch. The surface, chilled to hundreds of degrees below zero, is suddenly subjected to an immense energy input. The top layer of that frozen nitrogen snow doesn't melt. There is no liquid phase in a vacuum. It sublimates. It turns instantly from a solid into a gas, an explosive transformation. A shockwave of atmospheric rebirth would race across the hemisphere at the speed of sound. Our models predict the birth of a sublimation front, a wall of vaporizing atmosphere moving across the globe, triggering a barometric tsunami. The pressure would skyrocket from near zero to crushing density in a matter of hours at any given location. The silent world is shattered by the return of sound itself, a deafening roar that would accompany the very creation of a new sky. This is the planet taking its first breath after 2 years of being suffocated, and it is a violent, gasping breath. The rapidly expanding gas, heated by the relentless sun, would generate winds that would make the storms of the sunset seem like a gentle breeze. A chaotic, planet-engulfing tempest would rage for months as the newly formed atmosphere churns and seeks equilibrium. The nitrogen glaciers would not melt. They would fizz away like dry ice, unleashing 2 years of trapped gases back into the sky, feeding the maelstrom. Dust and debris frozen to the ground for years would be kicked up, creating global dust storms that would shroud the planet in a red haze. The sky once black would now be a churning, violent cauldron of pressure cells and supersonic jet streams. It is a rebirth, yes, but it is the most violent birth imaginable. A planetary-scale detonation that reinflates an entire atmosphere. And as this new atmosphere thickens, it creates a powerful greenhouse effect, trapping the star's heat. The surface temperature, once cryogenically cold, now soars to furnace-like intensity. The rock, which had contracted and cracked in the cold, now expands in the searing heat, grinding against itself, triggering planet-wide earthquakes, thermoquakes, as the crust adjusts to the new thermal reality. The world shrieks and shudders as it is forced from one extreme to the other. So we have this world of radical duality, a hemisphere of silent, frozen, airless perfection, and a hemisphere of scorching, storm-racked high-pressure chaos. And every 2 years they switch places. This isn't a cycle of seasons. It is a cycle of annihilation and recreation, a world perpetually caught between its own death and a violent rebirth. Which brings us inevitably to the most profound question of all. Could anything live here? Could life in any form we can conceive gain a foothold in a place so fundamentally hostile to stability, the chemistry seems impossible? The physics utterly unforgiving. Any organism on the surface would need to survive being flash frozen in a vacuum for 2 years, then pressure cooked in a supersonic hurricane for the next 2. It would need a biology that can withstand temperature swings of perhaps 500 degrees Celsius. It would need to handle pressures ranging from empty space to the crushing weight of a thick, hot atmosphere. On Earth, we find extremophils in the most shocking places in volcanic vents, in the depths of the Antarctic ice in acid lakes. But those are stable niches of extremity. This world offers no stability. It offers only the certainty of a coming apocalypse. Perhaps life could exist deep underground near geothermal vents, utterly divorced from the surface, living in perpetual darkness and warmth, ignorant of the celestial drama unfolding above. A hidden biosphere, a secret held in the planet's heart. Or perhaps life could be migratory. Imagine creatures perpetually on the move forever, living in the twilight zone, the terminator, that narrow strip between night and day. A global migration following the narrow band of habitable temperatures as it crawls across the planet's surface over 4 long years. An entire ecosystem, a food chain whose very existence is a pilgrimage, a race against a sunrise that brings fire and a sunset that brings ice. But then there is the most alien possibility of all. What if life didn't hide from the cycle? What if it embraced it? What if life evolved to use the cycle? Could an organism develop a form of natural cryopreservation? A biology that, as the great night approaches, could systematically shut down, replacing the water in its cells with a kind of biological antifreeze entering a state of suspended animation, a crystalline torpor. It would become part of the frozen landscape, indistinguishable from the rock, waiting for the shockwave of the dawn to trigger its reanimation. A phoenix biology born not of fire but of the deep abyssal cold. A life that has 2 states, one of stone and one of flesh. The challenges are monumental, perhaps insurmountable. The sheer destructive force of the atmospheric reformation alone seems like a barrier that no complex organism could ever cross. The very ground is too unstable, the air too treacherous. Yet when we look out into the cosmos, we are confronted again and again by the sheer tenacity of existence. Life is not a delicate flower. It is a stubborn weed pushing its way through the cracks in reality. The physics of this world are a testament to violence, its geology, a library of trauma. But it is in these crucibles, these places of ultimate stress, that the most surprising and resilient solutions are often found. The question is no longer a simple, could something live here? It has become far more complex and far more tantalizing. If we were to look, what unimaginable form might that life have taken to conquer the world of the 2-year night, and how would we even begin to search for it? So the models gave us the physics, the stark and unforgiving mathematics of this world's orbit. They sketched the ghost of a planet trapped in a celestial waltz of extremes, a place of radical, unforgiving opposition. But numbers on a screen, however elegant, can only tell you so much. They are the blueprint, not the cathedral. To truly understand, to walk upon the shores of this impossible world and feel its searing breath or its cryogenic bite, we had to do more than just calculate. We had to build it, not with steel and wire, but with light and logic inside the most powerful engines of computation we have ever conceived. We had to unleash our digital gods to forge a universe in silicon, a perfect high-fidelity copy of our distant enigma. The command is given and trillions of calculations per second begin their work. a virtual star ignites its simulated photons, flooding a digital sensorium. And through this electronic portal, we take our first step onto the surface. We arrive at the dawn of the long day, a dawn that will not yield to dusk for more than 2 Earth years. At first, it is deceptively beautiful. A soft golden light washes over plains of alien dust and frozen seas of nitrogen that begin to glitter, then shimmer, then weep. The first wisps of atmosphere sublimating from the thawing ground begin their slow climb into the sky. It is a planetary awakening, a resurrection on a scale we can barely comprehend. But this is a false spring, a treacherous and fleeting prelude to the inferno. Month by month the sun climbs higher, a malevolent eye that never blinks. It becomes a fixed point in the sky, a cosmic anchor holding the world in a state of perpetual escalating torment. The gentle thaw accelerates into a frantic boiling. Oceans of liquid methane and ethane, once placid, now churn in a furious frenzy, their surfaces erupting in geysers of superheated gas. The atmosphere, once thin and crisp, thickens into a soupy oppressive haze, trapping heat with terrifying efficiency. A runaway greenhouse effect kicks in not over millennia, as we fear on Earth, but over mere months. The temperature climbs past the boiling point of water, then past the melting point of lead. The very rocks begin to glow with a dull, cherry-red heat. You are standing now in a world-sized blast furnace. The sky is no longer blue or gold, but a searing incandescent white. The ground beneath your feet is semi-molten, a treacherous slag of silicates and metals. And the wind! The wind is a physical presence, a monster born from the colossal temperature difference between this hemisphere and its frozen counterpart on the other side of the planet. It is not a breeze or a gale. It is a continuous planet-spanning shockwave. Air superheated on this side to unimaginable temperatures screams across the surface at supersonic speeds, a relentless river of fire trying to reach the distant abyssal cold of the night side. This isn't weather. This is planetary physics made manifest as a form of ceaseless violence. No organism we know of, nothing built from delicate carbon chains and liquid water, could possibly endure this. The surface is not merely inhospitable. It is a sterilization chamber. Radiation from the star, unfiltered by a protective magnetic field, scours the land, shattering complex molecules. The long day is a great purifier, a blowtorch that patiently, methodically scours one half of the planet, erasing any possibility, any hope of life finding purchase on its sun-blasted skin. Our simulation confirms our deepest fears for 2 straight years. This hemisphere is a vision of hell, a testament to the fact that even in a star's habitable zone, a planet can be tortured into a state of utter lifelessness. The sheer, brutal persistence of the energy input creates a stable, but utterly lethal equilibrium. But the story of this world is one of 2 faces. As the simulation's clock ticks onward, our virtual viewpoint begins to move. We race across the molten plains, chasing the edge of this reality. Ahead, the boundary of night and day awaits. This isn't the gentle, forgiving twilight of Earth, a soft gradient of colour and peace. This is the Terminator Zone, the storm-racked seam of the world, and it is perhaps the most violent place on the entire planet. Here, the superheated high-pressure air from the dayside collides with the freezing thin atmosphere of the night side. The result is a perpetual globe-circling hurricane of unimaginable scale and fury. Winds exceeding thousands of kilometers per hour create vortices the size of continents. The sky is a chaotic canvas of lightning, not in isolated flashes, but in continuous strobing sheets that illuminate the pandemonium below. Here, the atmosphere itself begins to condense. Gases that were scorching hot just a few kilometers behind us now flash freeze in the encroaching cold. It begins to rain, but not water. It rains methane, ethane, nitrogen substances that are gases on our world, but here form a torrential cryogenic downpour. This deluge doesn't nourish, it shatters. It flash freezes the still glowing ground, creating vast cracked plains of exotic ice, a landscape of geological trauma. And yet within this maelstrom of violence, our models hint at the first faintest glimmer of possibility. For in this chaotic twilight zone, for a fleeting moment, temperatures might just pass through a range that is by some extreme measure habitable. Not stable, not peaceful, but survivable. It is a sliver of potential sanctuary, a moving oasis of chaos roaring between the furnace and the tomb. Could something evolve to live within the storm? A migratory organism perhaps forever surfing the edge of this planet, girding tempest, staying always one step ahead of the inferno and one step behind the deep freeze. The simulation cannot answer that, but it plants the seed of a radical idea that life might not require stability but could instead adapt to ride the very edge of chaos. Now we push through the storm wall. We leave the light, the heat, and the noise behind. We plunge into the great night, and the change is absolute. The simulation renders a world of profound, deafening silence. The winds, having dumped their thermal energy at the terminator, die down into nothingness. The star which dominated the sky for 2 years is gone, replaced by a spray of unfamiliar constellations, cold and impossibly clear in the vacuum-thin air. The temperature plummets with astonishing speed. We fall from hundreds of degrees above zero to 100, then 200 degrees below. The very air around us gives up its energy and solidifies. What was a torrential rain of liquid nitrogen at the terminator now becomes a gentle, silent snowfall. The last vestiges of the atmosphere crystallize and fall, blanketing the entire hemisphere in a layer of nitrogen and carbon dioxide snow dozens of meters thick. You're standing on a world entombed. The silence is not just an absence of sound. It is the silence of molecular motion grinding to a halt. It is the silence of absolute zero creeping ever closer. The ground is frozen solid for kilometers, down as brittle as glass. This is not merely a cold night. It is a cryogenic stasis imposed on half a planet. For 2 long years, this entire hemisphere is a ghost, a world paused, locked in the deepest freeze the solar system can offer. On the surface, then, the verdict is in. Life is impossible. The day is a furnace. The night is a cryo chamber. The transition between them is a blender. Our initial search for a habitable world appears to have found the opposite, a planet with 2 distinct, equally effective ways of destroying life. It is a profound disappointment, a confirmation that the universe is more often hostile than it is welcoming. The simulation seems to have given us a definitive tragic answer, but the simulation has not yet shown us everything. It has only shown us the surface, and the most resilient life on our own world has taught us a crucial lesson: when the surface is untenable, you go deep. With a command, our virtual camera abandons the frozen plains and plunges downward. We phase through the kilometers thick crust of rock and exotic ice, a journey into the planet's hidden heart. And here, in the crushing pressure and absolute blackness, we find the planet's saving grace: the core. Like Earth, this world is geologically active. Its core churns with radioactive decay and residual heat from its formation, a vast reservoir of thermal energy, completely independent of its distant, fickle sun. This internal engine, this planetary furnace, drives volcanism, and as we descend further we see it: a fissure in the deep crust, a geothermal vent. Out of this crack in the planet's depths billows a plume of superheated mineral-rich fluid. It is the planet's own internal sun, a localized source of heat and chemical energy that has been steadily flowing for billions of years, utterly oblivious to the drama of the furnace and the freezer playing out on the surface. Around this vent, the simulation predicts a pocket of stability, a haven of warmth. The water, yes, our models predict vast subsurface. Liquid water oceans insulated from the surface by the thick ice shell is kept from freezing. The temperature is stable. The chemical gradients are rich. It is in every way that matters an echo of the environments where life on Earth itself may have first begun. Suddenly, the entire equation of habitability is turned on its head. The sun, which we have always considered the primary arbiter of life, is rendered irrelevant. Here, life would not be photosynthetic based on light, but chemosynthetic based on the raw chemical energy pouring out from the planet's core. It would be a biosphere powered from within. Our visualizations, now guided by the principles of astrobiology, begin to populate this deep, dark ocean. We see vast mats of microbial life, bizarre ecosystems clinging to the rock around these vents, thriving in the scalding sulphurous water. We can imagine strange translucent predators hunting in the dark, navigating by sonar or by sensing the faint electrical fields of their prey. It will be a world of eternal darkness, eternal warmth, and eternal nourishment. Life here would have no concept of a sun of day or night. Its entire reality would be the vent a geothermal anchor in a lightless sea. The 2-year cycles of freezing and baking on the surface would be meaningless, a distant, irrelevant myth. The ice shell above which from the surface appears to be a feature of a dead world is in fact the greatest shield imaginable. It protects the ocean beneath from the radiation of the long day and insulates it from the lethal cold of the long night. The planet's greatest perceived flaw is in fact its ultimate salvation. The tombstone is a blanket. The prison is a fortress. The simulation expands, showing not just one vent, but a chain of them, a whole network of volcanic activity along tectonic plates deep beneath the ice. An entire global ecosystem, a hidden biosphere, could be thriving there. This planet might not have life on, it's so much as within it. It forces us to radically redefine our search parameters. We have been so focused on Earth-like worlds on planets with stable surfaces and gentle liquid water that we have been looking for our own reflection in the cosmos. But this world teaches us that the universe is far more imaginative than we are. It suggests that the true cradles of life may not be sun-drenched beaches, but the crushing, lightless abysses of worlds we would otherwise dismiss as hostile. The very concept of a habitable zone begins to dissolve, replaced by a more nuanced understanding of habitable locations. A planet might be a composite world, a place of profound contradictions, with some regions being utterly sterile, while others are teeming with hidden life. Resilience is the key. The resilience of a planetary system to maintain stable pockets against a backdrop of overwhelming hostility. This world is the ultimate test case. It has taken the worst that orbital mechanics can throw at it, the endless day, the abyssal night, and has, through the sheer fluke of its own internal heat, potentially created a sanctuary in its heart. It is no longer a simple question of is it habitable but where is it habitable? What does this mean for our search? It means we must learn to look deeper. We must learn to see planets not just for their surfaces but for their total systemic potential. We have been scanning for the wrong signals, perhaps. Looking for the green of photosynthesis, when we should have been looking for the thermal and chemical signatures of a world that is alive from the inside out. This simulation, this journey into a digital copy of a real place, has resolved the central conflict not by giving us a simple yes or no, but by presenting us with a breathtaking new paradigm. The tenacity of life, its ability to cling to existence in the most marginal of conditions, is something we have witnessed on Earth. But we have never dared to imagine it on a planetary scale like this. This world suggests that a planet can be actively, violently hostile on its surface, and yet be a cradle of life in its depths. The line between a habitable world and a dead one is not as clear as we believed. It is a blurred, complex, and far more hopeful boundary. The simulation ends, the virtual star fades, and we are left with the ghost of a world that has forever altered our perspective. We have stared into the furnace and the freezer and have found against all odds the subtle warmth of a possible genesis. The question now is no longer just theoretical. The models have shown us what is possible. They have given us a target. Now how do we look for the proof? How do we listen for the faint chemical whispers of a hidden ocean, an impossible biosphere across such an immeasurable gulf of space? And so we arrive at this final hard-won understanding, a complete portrait of a world that should not exist, painted pixel by painstaking pixel, using light from across the chasm of interstellar space. It is a testament to what we as species confined to a single fragile rock can achieve when we refuse to accept the silence, when we listen with unrelenting patience to the whispers of the cosmos. Think back to the very beginning of this journey. It wasn't a triumphant announcement or a stunning photograph. It was something far more subtle, far more human. A flicker of doubt in a sea of data, a single stubborn point of light on a graph that simply refused to behave as it should. A tiny, almost imperceptible dip in a star's brightness, a planetary transit so anomalous, so out of step with the neat clockwork elegance of every other system we had ever charted that the first instinct was to dismiss it as an error. A glitch in the telescope's optics, perhaps, or a cloud of interstellar dust playing tricks on our instruments. For months, that data point was a ghost in the machine, a nagging question mark that haunted the corridors of observatories. It defied the foundational laws of orbital mechanics as we knew them. Planets we were certain orbited their parent stars in a predictable gravitationally ordained dance. They spun on their axes, creating the familiar rhythm of day and night. But this world, this rogue data point, broke every rule. Its transit was too long, its reappearance too erratic. It was as if we had caught a glimpse of a gear in the cosmic clockwork that was profoundly and possibly broken. The debate was fierce, carried out in hushed tones over late-night video calls and across crowded conference halls. Was it two planets orbiting each other? A disintegrating megacomet, leaving a deceptive trail? Each hypothesis was raised meticulously modelled by supercomputers and ultimately discarded, crashing against the rocks of that one inexplicable observation. The simplest explanation that it was a single planet seemed to be the most radical of all. For it to be a planet, our understanding of how solar systems could form and function had to be fundamentally incomplete. It took the combined power of multiple observatories, each one a technological marvel in its own right, to finally begin solving the puzzle. We turned our greatest eyes towards that faint star, not just to watch for the dip in light, but to measure the gravitational wobble to pass the chemical fingerprints hidden in its spectrum. Slowly, painstakingly, a new picture began to emerge from the noise. The data revealed not one, but two stars locked in a slow, majestic waltz with one another. And our planet was not the child of one, but the captive of both. This was the key, the revelation that unlocked everything. The planet we'd found was not tethered to the star it appeared to orbit. Instead, it was held in a state of gravitational escrow, tidally locked not to its nearby sun but to the distant companion star. Imagine a child on a carousel, but instead of looking at the centre pole, they are staring fixedly at a person standing far outside the ride. As the carousel spins, the child is carried around, yet one side of their body is always facing the distant observer, while the other is perpetually turned towards the ride's interior. Our planet is that child. One hemisphere forever faces the dim companion star itself, a distant point of light. The other hemisphere perpetually faces its primary sun, the brilliant furnace that should by all rights be its master. As the planet makes its long looping journey around that primary sun, this bizarre tidal lock holds it in place like a cosmic gyroscope. The result is a day and a night of unimaginable length. For 2 long Earth years, one half of the planet is baked under the unrelenting gaze of a star that never sets, a perpetual searing noon. Then as its orbit carries it around, that hemisphere slowly turns away, plunging into a night that also lasts for 2 full years. A darkness so profound, so absolute, it would make our own midnight feel like a blinding dawn. What we had found was not a glitch in the data. It was a rupture in our imagination. Science fiction has given us worlds of endless desert planets, of perpetual ice, even gas giants with diamond rain. But the universe, it turns out, is a far more creative author. It presented us with a world cleaved in two by time itself, a planet of absolutes, a kingdom of endless day and an empire of unending night, a place where the very concept of a daily cycle, the rhythm that has guided every form of life on our own world, is utterly meaningless. It serves as the most powerful reminder that our models of the cosmos, our neat and tidy theories, are not laws the universe must obey. They are merely our current best sketches of an infinite canvas, and out there in the dark are masterpieces we have not yet even conceived of. This discovery does more than just add a new exotic specimen to our celestial catalogue. It fundamentally alters the very questions we ask. It is a signpost pointing us towards a new, more nuanced understanding of the cosmos and our place within it. For decades, our search for extraterrestrial life has been anchored by a simple concept: the habitable zone. That narrow temperate band around a star where liquid water, the essential ingredient for life as we know it, could exist. We have been searching for reflections of Earth, for pale blue dots orbiting yellow suns at a comfortable familiar distance. But this world with its 2-year night tells us that this Goldilocks model is perhaps tragically simplistic. It forces us to ask new, more profound questions. Is habitability merely a function of temperature? Or is it something more complex, a dance between geology, atmosphere, and the strange gravitational tides of an entire system? This planet likely possesses an atmosphere, a thin veil struggling against the extremes. During the long day, it would be a cauldron of superheated gases with winds faster than the speed of sound screaming across continents of molten rock. As the Terminator line, that slow-moving twilight, begins its 2-year creep across the surface, the temperature would plummet by hundreds of degrees. That same atmosphere would freeze snowing out onto the landscape, blanketing it in exotic ices of nitrogen and carbon monoxide, forming glaciers that would flow and crack under a sky of blackness punctuated by the distant cold light of its gravitational anchor. Could life exist in such a place? Our terrestrial biases scream no. But the universe has a habit of ignoring our assumptions. Perhaps life on such a world wouldn't be a constant presence but a cyclical phenomenon on a planetary scale. Imagine spores or microbial cysts frozen deep beneath the nitrogen ice, protected from the vacuum and the cold for 2 years of night. They are dormant, waiting. Then, as the first rays of the long-awaited dawn touch the ice, the thaw begins. Not a gentle spring, but a violent, explosive sublimation, where frozen plains turn directly into a thick, temporary atmosphere. In that turbulent, fleeting season, life might bloom. A frantic, accelerated race to grow, to reproduce, to store energy, before the long twilight once again signals the coming of the Great Freeze. It would be a form of planetary hibernation, life not as a steady state, but as a recurring miracle, a biological echo of the planet's own extreme orbit. Discovering such a world shatters the cage of our expectations. It tells us that we must broaden our search to look for life, not just in the gentle cradles of space, but in its most violent and unpredictable crucibles. We must begin to search for biosignatures that are not constant but transient. Glimpses of a methane or oxygen that appear and then vanish over the course of years, a planetary breath taken only once every half-decade. This planet is a lesson in humility. It teaches us that in our quest to find life, we must be prepared to find a form of existence so alien, it challenges our very definition of what it means to be alive. And to answer these new, more daring questions, we will need new, more audacious tools. The telescopes that made this discovery possible are the pinnacles of human engineering, but they have already shown us their limits. They allowed us to infer this world's nature, to sketch its portrait from the clever interpretation of shadows and light. But we want to see it. We want to move beyond the graph and the data point, to capture a direct image, to resolve this impossible world as a tangible place. This one discovery has already become a powerful catalyst, a driving force behind the next generation of space observatories. We are now designing telescopes with mirrors so large they will have to be assembled in space by robots, instruments so sensitive they could detect the heat from a single candle on the surface of the moon. We are developing Starshade's colossal sunflower-shaped spacecraft that will fly thousands of miles in perfect formation, with a telescope precisely blocking the glare of a parent star so that we can photograph the faint reflected light from its planets. These future observatories are no longer just dreams on a drawing board. They are the direct response to the challenge this planet has laid before us. It has shown us a mystery that we cannot in good conscience leave unsolved. We need to be able to collect that planet's light, to spread it into a rainbow of its constituent parts, and to read the story written in its atmosphere. Does it hold water, vapor, carbon dioxide, methane? Does it possess the telltale chemical imbalances that could only be produced by a global active biology? These are the questions that will be answered by the engineers and scientists of tomorrow, inspired by the wonders we are uncovering today. Every time we find a world that breaks the rules, we galvanize a new wave of innovation. We push our technology not for its own sake, but in the service of one of humanity's oldest and most noble pursuits, exploration. We are building these new eyes not just to find more worlds like our own, but specifically to find the ones that are nothing like it, because they are the ones that have the most to teach us. This planet with its 2-year night is a perfect embodiment of that principle. It is a gravitational anomaly, a climatological nightmare, and a profound philosophical puzzle. And for all those reasons, it may just be one of the most important discoveries we have ever made. Ultimately, this entire journey from a single, perplexing photon captured by a telescope to a comprehensive understanding of a world hundreds of light years away is about more than just astronomy. It is a reflection of the human spirit. It is a story about our innate, unquenchable need to understand. to look out into the great intimidating darkness of the cosmos and not be cowed by its scale, but to be inspired by its mysteries. We are pattern seekers, storytellers, puzzle solvers. It is the very essence of who we are. The same impulse that drove our ancestors to chart the seasons and to name the constellations is the same one that now drives us to build billion-dollar machines to hunt for alien worlds. The existence of a planet with a 2-year night does not diminish our own world. It enriches it. It provides a vital context for our own existence. It reminds us that our Earth, with its gentle axial tilt, its stable orbit, and its fleeting 24-hour days, is not the default. It is a cosmic exception, a precious, perhaps even unique sanctuary in a universe that is far more varied and violent than we ever imagined. This discovery is not an endpoint. It is a doorway. We have found one impossible world, a testament to the universe's boundless capacity for surprise. Now we must face the most exhilarating and humbling question of all. How many more are waiting for us? How many other impossible planets governed by rules we have not yet even begun to imagine are circling those quiet, unassuming points of light we see scattered across our night sky? The search will continue. With every new observation, with every new world we add to our maps, the grand, astonishing tapestry of the cosmos becomes a little clearer. We may never have all the answers. We may never fully comprehend the sheer scale and diversity of existence, but we will never stop asking the questions. We will never stop looking up, because in that endless patient search, we find not only the secrets of the universe, but the very best measure of ourselves.